So yeah, as mentioned, I'm working for Cohere. What we're doing is one of the few companies that are training foundation models and providing them as a service. My colleague Phil, he's training a generate model. So we all know them. You give an instruction, a command in, like write me an essay about the French Revolution, and then it generates you the output. It appears that you can also use generative models also for other interesting use cases like summarizing, rewriting. Quite popular is like extraction of like structured data. So how can you go from unstructured to structured data? And what I'm doing at Cohere is training text understanding models. Strong focus is on search. So how can you find in like a large stack of data the really relevant and interesting information, which is like far from solved. And yeah, one really strong use case for us is like bringing text understanding and generate in like an enterprise setting. So if you ask like an out-of-the-box generate model, what do our employees think about our benefits, or what have we discussed with client X so far? Luckily, the generate model out of the box is not able to answer this correctly. So what people find really interesting in the enterprise setting is like combination. So you ask a question like, what has been discussed with client X so far? What should I follow up? You put this into like a search system. So you connect all your enterprise data to like some central access point. You analyze the results you get from the search system, and then you plug it into your generate model. And then you get an output like, hey, you have discussed with so far with the client. In the next meeting, you promise to follow up on. However, we all know search works quite terrible. So if we exclude Google and we use like search in like a PDF or in a Word document, it works terrible. And then if you scale it up to like hundreds, thousands, millions, billions of conversations, documents you have in an enterprise, it's sadly not working well. And so this is like a strong focus of mine. How can you improve search? Because yeah, it's critical for this pipeline. So just if you find like the information, what have you discussed with the client so far, the model can generate like a good summary or action items, which is a suggestions based on that. For a really long time, people in the search field, they have been using lexical search. And in lexical search, what you do is you take your text, you break it down into words, and then you use like a bag of word representation. So like every word is some position in your vocabulary. Let's say you take like a 1 million size vocabulary, and then the word cat is, for example, on position 1, the word bike is on position 2, the word cats is on position 3. But here we already see the challenge that they all have the same distance. So in like these representation for the computer, in a bag of word representation, the distance from cat to cats and cat to bike is the same. And if you search for cat and the document contains cats, you don't find this result. So probably you all experience this when we search, like do keyword search, lexical search. We're not able to find the relevant information if we're not taking into like the plurals or suffixes of words into account. So a common solution you find in lexical search is to use stemming. So you take the word cats, you remove the suffix s, and you just map it to the same word cat. It works kind of okay, but you have certain cases. For example, there's a company Whitings. If you remove the suffix, if you do some stemmings, it's reduced to the word with. And then if you search for the company Withings, it will find all documents containing the word with, and then the search results are, yeah, sadly bad again. Second challenge with lexical search is like spelling variation. For example, British and American English. Here again, the word color and then the American English and the British English color. These are two completely distinct words. And again, the word color from British English to American English has the same distance as, for example, bike or any other word. So what you often do in these lexical search setups is you create synonym lists. So you create like a big bunch of lists where you say, okay, the word color and color should be mapped to the same. USA should be mapped to United States of America. NY should be mapped to New York. And then you try to keep the synonyms list up to date. Challenge is, we know synonyms are added. Synonyms can be ambiguous sometimes. NY can refer to New York, but in other cases, NY can have like probably a lot of different meanings. And then, yeah, the results can become like really strange if your synonym list is not matching the content of the text. Then in lexical search, we have the challenge that, yeah, some words are really hard to spell correctly. So here we have like 2 users looking for some vacation. They want to go to like Honolulu. So they try to search for like Honolulu, but there's like no results. So they try an alternative spelling, Honolulu. Sadly, also no results. So they back up and try to search for Hawaii. But again, they misspell Hawaii. And then they just give up. So we all know this painful experience. So what you do in a typical system is like you add spelling corrections. So if someone inputs Honolulu like this, you say, hey, did you mean to search for Honolulu? And here are the results for Honolulu. And then finally, there's a challenge of like ambiguous words. We all know apple. Apple can refer to the fruit, but it can also refer to the company. And if you have something like apple pie and apple store, apple in both cases refer to the same entry in the vocabulary. Even such, these are like completely different. And yeah, in lexical search, you just ignore it. So if you search for like apple pie recipes, you might find like recipes how to fix your Apple computer. And sadly, as mentioned, search works really terrible. So if we look outside of Google and the other big search engine and go to like Wikipedia, one of the most popular websites on the earth, and you do like a really simple search query, you ask, what's the capital of the United States? In the background, they run some lexical search. They search for articles containing these words, and then the top article containing these words most frequently is the article about capital punishment in the United States, because it contains the word capital, United States, the, is. And yeah, according to lexical search, that's the best match you can get. And the article about Washington, D.C. is just not even on the first page, not among the top 20 results. So you have to like click really through to the next page, to the next page, to the next page to find the article about Washington, D.C. And yeah, it's kind of like a trivial search query, which one of the most popular websites is not getting right due to lexical search. And then besides all these challenges, you can make it even worse if you have to do it in like more than one languages. So in English, we know we can tokenize based on white spaces. So nicely, we put like a space between words. This works for English, but for Chinese, it doesn't work. And then, as mentioned, we have like the stemmer that removes like suffixes. For English, we have stemmer, but for Spanish, stemming is different. For German, stemming is different. For Chinese, stemming is different. Until you remove stop words. So each language has different stop words. Each language has different synonyms. Each language has different spelling mistakes and spelling corrections. And then these all need to go to like individual indices, which you need to manage, maintain, and scale. And yeah, if you're like Wikipedia, you have to do it like for, I don't know, 200 languages, 300 languages. Also other popular websites where you have like audience of 100 languages. It's a really, really painful process. And sadly, a lot of companies, they just put like some effort to optimize like the English search approach. So if you search in English, it works kind of okay by removing suffixes, adding synonyms, adding spelling correction. But then they say, okay, the market share for the other things, it's just too fragmented. So non-English for a lot of enterprises, like 50% of the customer base, it's like too fragmented, so they don't put like any effort in it. And then if you search in Spanish, Portuguese, German, Chinese, Korean, it's even worse than the English search. So definitely we need better approaches for this. One approach I've been working on for quite a long time, since 2018, for the past 5 years, is so-called semantic search. So we all know from the early 2000s, you can use these vector spaces to represent words. So we have like the word color, color, and colors. We put all them close in the vector space. Same cat, cats, and kitty. And cat is related to dog, so we also put it close here. And then we have apple pie and apple store, but because they refer to different things, we put them distantly in the vector space. And yeah, I've been working a lot on like, how can you use this better, more intuitive representation of words to build really powerful search systems out of it. And it works really well. So if you search for, like, on Wikipedia, what's the capital of the United States, as mentioned, top hits by keyword search is about capital punishment, then about Ohio, because it's a state in the United States and has capital, and then Nevada, it's one of the United States states and it has capital. If you flip it to semantic search, you get the right results. Washington, D.C. is the capital of the United States, because the model knows, okay, if you search for the capital of the United States, that's closely connected to Washington, D.C. It can take the word order into account, so it gives you much, much better results. And how do these approaches work? So the idea here is to use vector spaces. So what you do is you take all your Wikipedia articles or whatever data you have, you put them into a vector space, and then when a query comes in, what's the capital of the United States, you also project it to this vector space, and then you look for the closest matches in this vector space. And here in this case, for example, if the query is like, what's the capital of the United States, this might be the article about Washington, D.C. To put it a bit more in like technical terms, what you do is you have a transformer network like BERT. You pass in your query, you pass in your document independently into the transformer network, and then BERT gives you contextualized word embeddings at the end, which you can then do at a pooling operation, like, for example, take the average of all word embeddings, and this gives you like some fixed size vector, which you can then, for example, compare with cosine similarity to get the similarity between these two vectors. And then it tells you, okay, how similar is the document to the query? And this allows you to build a search system on this. And what's nice about these vector spaces, it's not grounded in words, and words can be really different depending on languages, and grammar can be really different. But these vector spaces, they can be like unique, like a lingua franca, and you can map like different languages to the same point. So you can map like two dogs in the snow, and the German Zwei Hunde im Schnee, and the Spanish version and the Chinese version. They can all be projected in the same spot. And then you're able to search across languages. And on the one side, it has two really cool things. First, it makes all your stack in search a lot easier. So your documents and queries can come in like 100 languages. You have this one embedding model that's able to search across languages. You put it in a vector database. You no longer have to do like differentiation between languages. You don't have to find like synonyms and spelling corrections for each language individually. You don't have to decide which language this document is in. So especially like in mixed language where people mix, I don't know, let's say Hindi and English together, you don't have to decide, okay, is it a Hindi document and needs to go to the Hindi pipeline, or is it an English document and needs to go to the English document? So it's like extremely simple nowadays to build like a good search system across 100 languages, which is like really easy to deploy and monitor. And every improvement you do on this pipeline is beneficial for like all the hundreds of languages. What's really cool is, in my opinion, the ability to search across languages, because the search no longer works on words, but on these vector spaces. So you can input like an Arabic query, what's the capital of the United States? You put it into like the English Wikipedia. And yeah, keyword search obviously doesn't retrieve any sensible results, because in the English Wikipedia, then there are not that many Arabic articles. But because this is like disconnected and first projects it to the same point as if you would search for like what's the capital of the United States, you get the same results about Washington, D.C. As the capital of the United States. And it's an extremely cool and nice feature to play around with for multinational enterprises, for like financial domain where you want to see like information across languages. To get a bit more technical, how do we train these embedding models, be it like in one language or across languages? So one approach that's really fundamental is the so-called contrastive training, or also multiple negative ranking loss. So here the idea is you have certain set of positive pairs, A for anchor and P, and you have like a long list of these pairs. And this can be, for example, the query and the answer passage. It can be a question and duplicate question, or it can be the title of a paper and the abstract of a paper, or the query and the product someone purchased in an e-commerce setting. And what you want is like that these pairs are close. So A1 and P1 here, this should be close in the vector space, and all the other points, all the other P's should be distant. So A1, P1 should be close, and AP to AP5, A1 to P5 should be distant in the vector space. And yeah, to give a bit more intuitive explanation, you can think about like a multiple choice exam. You have, for example, your anchor is a question, how many people live in Berlin? And then you have like different P's. First is like around 3.5 million people live in Berlin. Second one is Washington, D.C. is the capital of the US. And third is like 21 Olympics are held in Japan. And like in school, like a multiple choice exam, you ask like, okay, which pairing is correct? And so in terms of vectors embeddings, what you do is you compute the text embeddings for all A and P's, and then you compute the similarities. So you say, okay, similarity between A1 and P5 is 0.5, 0.3, and 0.1. And then you compare this. So you say, this is my prediction. I have like a similarity of 0.5, 0.3, and 0.1. I know only the first one is correct. So A1 and P1 should have like highest possible similarity. All others should have like a 0 similarity. And then you use cross-entropy loss as you do it like with classification training. You say, this is your prediction, this is the correct answer. And then you do backpropagation on this. So it's kind of like easy, really powerful, can be used in like many settings once you figured out like, okay, what should be close in your vector space. One nice trick to improve search quality is to use larger batch sizes. This is similar to like a multiple choice exam. So if you give like 4 answer possibilities to a multiple choice exam, there's like a 25% chance to get it right by random. If you increase it to 100, it's a lot harder to get it right by random. And what we see here in the paper, we see here the number of random negatives. So how big is the batch size? And then we see here the performance on downstream tasks, like how good is the model? And as we see up to a certain degree, like 8,000 examples, the model constantly improves. So that's like a really nice, easy trick to make the model better and better. It's a bit challenging because the bigger the batch size, the more GPU memory you need. And then quickly you run out of like GPU memory on a single GPU. And then at some point you run out of GPU memory on like a single GPU server. And then you have to come into like a distributed training, which make it like challenging again. The other easy trick is hard negatives. So similar as in a multiple choice exam, if you have like a question like here, it's like really easy to get the answer right, even if you don't know like how many people live in Berlin, because P1 is the only one that's talking about people living somewhere, living in Berlin. So that's really trivial. The other hard negatives would be you add answers to possible candidates to it, which look like really similar to the correct answer, but it's not like factually wrong. And so what you do is instead of like taking these pairs, you start with tuples, that you say you have an anchor, you have a positive, and you have a hard negative n. And the n should be similar to p, but it should not match with a. So a good example would be like how many people live in London, and then you say, okay, this positive is around 9 million people live in London. The hard negative would be around 1 million people live in Birmingham, second to London. So this negative is similar to the P, but it's obviously for us as a human not correct. So we as a human, if we see like, okay, these two, we can obviously say, okay, which one is correct? P is correct, N is incorrect. A bad example, however, would be the following: how many people live in London? And then you have a positive around 9 million people live in London. And as negative, you would put into like London has a population of 9 million people. So we call this also like a false positive. False negative. So we would say, yeah, both are correct. However, we train the model to say A and P should be really close in the vector space. A and N should be like really distant in the vector space. And then the model is like really confused. Okay, why is P better to A than N? And then it comes out with like really weird behavior, trying to figure out, okay, why should this be like better than the other? Is it due to like the length, the number of words in the text? Is it how it starts the sentence? Is it how it ends the sentence? And in general, you see models extremely suffer. Until you don't create these triplets by hand, because models often train on like billions or millions to billions of these triplets. So it's like completely infeasible to do it by hand. And so you have to have processes to ensure that the negative is like really, really good, really close to the positive, but it's not answering the or not matching the anchor. Okay, back to multilingual cross-lingual embedding models. It's kind of like a long way or long interest in the community, in the research community. The first models from Facebook, Laser, they started with machine translated models. So they used like an encoder, decoder, LSTM network from machine translation, and then used the output embedding from the encoder as a vector. In 2012, I presented multilingual knowledge distillation, which is, I think, a nice and easy trick to expand monolingual, for example, like an English model, to many, many languages. And what you use is like you use parallel data from machine translation. You have your teacher embedding model that's producing good embeddings, mostly for English. And then you feed in your parallel data. So the English goes to the teacher model. This gives you some sentence vector. The English goes also to the student model, and the German also goes to the student model. This gives you a vector for the English text and for the German text. And then you say, okay, this all should be really close. So you say, okay, the teacher model, that's the correct point. The English vector from the student should be also close, and the German vector should also be close. So you use here mean squared error loss to say, okay, these vectors should be close, and the further distant they are, the higher the loss. And then you can optimize, tune the student model, and get like a really quickly good model. It's also really nice because you can extend easily like any model. For example, you have the English clip model, and then you can just use this process to make like a multilingual version out of this model. The other option is to use multilingual constructive training. So the previous approach was mainly based on alignment, where you had like an English model, and then you align like a multilingual version to this English vector space. But the issue is here, if you do this, then the multilingual model knows in 100 languages questions about the US tax system. So which forms do I need to fill in to get like a tax reimbursement on my home purchase, whatever. But it doesn't know about other languages and country-specific topics. So it has never seen questions about how to do taxes in Germany or how to do taxes in Korea. And what you can do instead is like use constructive training, but here the question, like, how do you get question and answer pairs in 100 languages? So not like only like English question and answer pairs with a strong bias on the US, but really question and answers from people in Germany, in France, in Korea, in Japan, on topics they're interested in, with answers that match their local environment. And so what we did last year, we went to the web. So we crawl a large set of question-answer pairs from the web. First step is to remove irrelevant pairs. So you have you find a question, but then there's this cookie consent banner, or you have a question and there's these please sign up with our website page. So you remove these. Challenge here in English, it's straightforward to do, but if you do it on hundreds of languages, you don't really know how does a cookie consent banner in China or Japan or Korea or on Arabic look like. Then we extend it to triplets. So we take the question, we have the answer, then we find some in a big pool of possible answers, negatives that look really similar to answers. And we take these billions of triplets and clean them really thoughtfully. On the one side, false positive, where you have a question and the answer is not really meaningful or not helpful. And remove the negatives where you have a question and answer, but then the negative is not a negative, but also a valid answer to the question. And so here you need to find processes to scale it up to billions of these triplets, where you typically use more powerful models. So you train bigger models to tell you, okay, look at this triplet, tell me, is it a good triplet or not? And then you do this to clean your data. And at the end, we ended up with close to 1 billion English triplets, close to 500 million non-English triplets. And then it's easy. You do this contrastive training with negatives, with large batch sizes, on a lot of GPUs. And then, you get a nice model at the output. What's interesting from a scientific point of view is language bias. So this has been a long discussion we had. How much language bias should we have in the embedding model? So language bias describes that certain language combinations are preferred. So for example, there's from Google a model called LABSE. If we look at English vectors in red and Russian vectors in blue, we see kind of a clear separation between these two vector spaces. So all the English vectors, all the English text is over here, all the Russian text is over here. Compared to other models, Laser, MUs, SBIRD, they have fewer language bias. And so model with language bias, for example, if you search in English, prefers retrieving English documents over other documents. And typically in our community, we say, okay, bias is bad, we should object bias, but it's sadly not so easy with language bias. So if you don't have language bias, let's say you have a perfect model, doesn't look at all at the language. So what are the possible negative effects when you have a language bias? So if you have a language bias, same language results are ranked higher just because of the language, and there might be better hits or answer in other languages. There are some arguments why you want to have a language bias. It can be user preference. If I search in German, I might want, German passage is totally preferred over an Arabic, Chinese, Japanese passage from reading it. Also, there's a higher confidence by the model, so it's easier to compare query document in the same language for relevance than if it's in different languages. Same with annotators. If they get a German query and a French document, and they need to say, okay, is it relevant or not? Is it really matching exactly what's asked in the query? It can be really hard to assess this, and it's much easier if it's both in the same language. There are also some negative effects if you don't have a language bias. So maybe you say, okay, you don't want a language bias. Your users are fluent across languages. You want to retrieve the best possible answer to it. If you do it in a multi-model setup, let's say text to image, and you search for the word wedding, you find an image of, image like this. So you have a girl in a white dress, a man in his black smoking, white skin, smiling at each other, throwing flowers. So that's totally how weddings are celebrated in the Western world. If you now search for wedding in Hindi, the model doesn't know that the input is Hindi. It's mapping this Hindi word to the same point for wedding. And your image search system gives you the same picture, but maybe it's safe to assume if someone searches in Hindi for wedding, they are not so much interested of pictures of a wedding celebrated in the West, maybe more like, okay, how is it celebrated? Where Hindi is primarily spoken, so how is it celebrated in India? Similar, if I ask like, who is the president? My answer, which I'm looking for, is like, yeah, Joe Biden is the current president. If I ask the same question in French, who's the president? If the model doesn't know that this is like formulated in French, it will retrieve the same passage that Joe Biden is the current president. But probably someone asking this in French is not so much interested on the US president, it's more interested in the French president. And then if you have a model without like any language understanding, yeah, questions like, okay, which biases should you encode in it? Like when you ask about the president, should it be the US president, French president, someone else? Weddings, if you search for wedding, is like how a wedding is celebrated in the West or in Arabic countries or in India or in China or Japan. So these are like really, really hard questions. We did some evaluation on cross-lingual retrieval. Sadly, there are like not that many good data sets available. So it's like really new, interesting research direction, but evaluation is completely absent. So what we did is like we machine translated documents from Track Deep Learning 2019-2020. So these are originally queries from the US English search query, and we translated it to like different languages. Here just depicted mixture in Arabic, and we have like different setups where we say the query language can be English or Arabic. Document language can either be all English, all Arabic, or like a mixture 50-50 English-Arabic. And we see English, that's the baseline. So first stage is an embedding approach, which I just talked about. If the model would be perfect, work perfectly across languages, not have like any language bias, we would expect in all settings like a performance of 71. NDCG at 10, so higher, the better the search quality. But if we go to Arabic, we see, okay, there's like a drop in search quality, given that the model has seen a lot less Arabic search data, training data. So this is normal, expected. And then if we mix the document languages to like 50-50 English-Arabic, we see that performance drops even further, with the worst drop in like Arabic. However, we have also like a second stage approach, a re-ranking approach, which is using like a more powerful concept than embeddings. And here we see that the language bias is not that present. So we see English works the best again. Again, due to like amount of training data available. Arabic is much closer in terms of search quality. And then if you do like this mixture, you see, okay, they are all like really close. So this is like really nice way. If you wanted to say, okay, I don't want to have like a language bias in my search engine, and like any language should just be matched on quality. To summarize my presentation, semantic search is amazing for multilingual setups. Before with lexical search, it's painful as you have to configure and tune and maintain and scale pipelines individually on languages and then across like hundreds of languages. Now you can use with semantic search the same pipeline for all languages. Enables cross-lingual search, so that's quite helpful at multinational companies, but also in my previous research group at the university. 50% of the PhD students could speak German, 50% could not speak German. Sometimes documents were in German, sometimes documents were in English, and that was always a bit hard to like, okay, did I communicate in German or did I communicate in English? And then you wouldn't need to know this before you formulate your search query. Similar in finance, when you wanted to find relevant information on markets and market player across languages. In forensics, if you investigate, okay, I don't know, terrorist cells, and you don't know in which language they are communicating. So it's quite helpful if you can just search and then tells you, okay, here are the relevant results, independent of the language people are communicating. Research challenges exist. First big challenge, like how can we achieve the transfer between languages? So in English, we have, as you've seen, like a billion training triplets, but for other languages, it's a lot fewer. And then the lower resourced languages, the fewer examples you have. So how can we take the information, the knowledge we learn from English and transfer it to other languages? And second question is on language bias, like how much language bias do you want to have? How do you model it correctly? How can you still give the best answer to a query, still taking the language of the query into account so that you can be aware of like certain preferences like French president, US president into account. So how can you control this? How can you modify it and say, okay, for this use case, I don't want to have like any language bias. If you do like recommendation of, let's say, podcasts, and you know, okay, this user is fluent in these languages, you don't want to have like any preference in language bias. But for others, you want to have like some bias in terms of language. That's so much for my side. Yeah, looking forward to questions you might have.